You plug in, watch the kilowatts climb, and still get less range than numbers promised. Invisible systems are quietly stealing your charging power, and most owners never notice. Today, we are exposing the silent energy thieves inside every electric car, parasitic loads. These are the background systems: cabin heating, battery thermal loops, infotainment, telematics, even sensors that never fully sleep, that siphon off valuable charging power while you think you're actually charging. I'll show the real numbers, the real world impact on level 2 and DC fast charging, and simple moves you can do tonight. By the end, you will know what to watch, what to change, and how much money and range you can save. Hello everyone, I'm Shayan, an engineer specialized in electric vehicle development. What's parasitic loads actually? Parasitic loads are any electrical draw that doesn't directly move the car forward. Think of them like small faucets beside your main tap. Individually, many of these draws are tiny, a display here, a sensor ping there, but together they can become a real slice of the incoming power while charging. The big categories are thermal systems like HVAC and battery climate control, drive-related ancillaries like cooling, pumps, fans, infotainment and displays, telematics and security systems, lighting, and slow standby drains when the car is parked. These systems operate during charging and at rest, and their combined effect can be surprisingly large. Research and testing across labs and owner communities repeatedly show that auxiliary systems can consume kilowatts under real conditions and measurable wattages in standby. Thermal systems are the single largest parasitic drain. Heating in particular can suck a lot of energy because you're using electricity to raise cabin temperature and to warm the battery pack. Depending on vehicle size, installation, ambient temperature, and heating method, heating demands can range from under 1 kilowatt when a heat pump is used gently up to 4 to 8 kilowatt or more for resistive heaters in cold climates. That's a huge number when you remember many home level 2 chargers deliver around 6 to 7.2 kilowatt. In plain terms, if your heater draws 4 kilowatt while your charger is only putting in 7 kilowatt, a large chunk of the incoming power is going to heat instead of the battery pack. Laboratory data show typical cabin heating power can run roughly 1.8 to 3.7 kilowatt during winter's operation for many EVs, while other analyses report typically needs of 4 to 8 kilowatt depending on the conditions and vehicle size. That range explains why owners see massive winter range drops and why charging can feel painfully slow in the cold. The Stealthy drains: infotainment, sensors, and standby electronics. Smaller systems add up: modern infotainment stacks, instrument clusters, telematic modules, USB phone chargers, and LED interior lights each draw power from tens to a few hundred watts. Typical infotainment systems and screens often use 50 to 150 watts. Instrument clusters and displays add another 30 to 100 watts. Phone charging is small but persistent at 5 to 15 watts. Put them together and you can easily have 200 to 500 watts of continuous draw while the car charges. Relative to a 7.2 kilowatt level 2 feed, that's 3 to 7% lost right there. And on public DC chargers, that number compounds with other losses and fees. Community tests and component power lists back those figures up. Vampire drain or phantom drain is the energy loss while a car is parked and not charging. It comes from security systems, remote monitoring, cell connectivity, and periodic wake-ups for telemetry or OTA updates. Large citizen science data sets and telemetry research show that modern EVs typically lose less than 1 to 2% of the pack capacity per day when parked and not in sentry or several other active modes. But that number climbs if you leave features active. For a 60 kWh battery, 1% equals to 0.6 kWh. Not huge day to day, but measurable over weeks and costly when you're relying on every last mile. Recurrent Auto's vampire drain experiments and fleet data give a detailed look at these passive losses and how much features like sentry mode or frequent app pings add to the drain. How parasitic loads hit charging efficiency and range. Let's make this concrete. Suppose you're charging on a common level 2 supply that pushes 7.2 kilowatt. If HVAC and thermal system draw 2 kilowatt and infotainment plus a standby draw of 300 watts, that's 2.3 kilowatt consumed by ancillaries. The battery sees only 7.2 minus 2.3, like 4.9 kilowatts net. That's a 32% effective loss of the face value incoming power. On a 7.2 kilowatt charger, that turns a 1 hour top up into 1.5 hour process to get the same kilowatt hour into the pack. On DC fast charging, the effects are different but still real. The car can alter charge current to maintain thermal control, meaning your expected peak kilowatt plateau drops and your 10 to 80% session stretches. Real test data show preconditioned batteries accept 30 to 50% more peak power and shorten total charge session minutes. Conversely, cold packs or hot packs force early tapering, shaving delivered kilowatt and extending stop times. Use those numbers to understand why a charger rating often fails to match delivered energy without proper thermal management. Why most owners don't notice it and why OEMs don't scream it from the roof. Parasitic losses hide behind dashboards and clever UI. Your car shows incoming kilowatt, your app shows percentage charged, and your charger shows session power. But the split between what arrives and what actually stores in the battery is invisible unless you log it carefully. Manufacturers focus on range and peak charging specs because they can sell cars. They don't emphasize how HVAC or sentry mode can cut effective charging throughput because that would confuse marketing. The result? Owners are surprised when charging takes longer than advertised or range falls faster than expected. And many blame the charger or the battery rather than the invisible auxiliaries. Research and utility reports recommend transparency and driver education because small behavior changes like preconditioning while plugged can reclaim energy that would otherwise be wasted. Let's look at few representative numbers to bring the problems home. Winter heating load. Tests and data show electric heating power consumption for cabins commonly runs from 1.8 to 3.7 kilowatts in cold, depending on the vehicle and heating technology. Heat pump vehicles do better, but worst-case resistive heating can easily be 4 to 8 kilowatts. For a driver charging at home on 7.2 kilowatt, resistive heating can consume more than half the incoming power while you're charging and warming the cabin. That's why some winter charging sessions may seem to crawl. Vampire drain. Recurrent and community studies show typical park loss under conservative settings is under 1 to 2% per day. But sensory modes or heavy telematics can push that higher. For a 75 kWh pack, 1% is 0.75 kWh. Not nothing if you're away for days. Accessory draws, infotainment and displays at 50 to 150 watts. Instrument clusters between 30 to 100 watts. And small pumps or fans potentially more mean a steady background of few hundred watts. Over a 2-hour charge, those draws can eat a kilowatt hour or more. Community power measurements write-ups show roughly the scale of draws across many models. Parasitic loads hurt in 3 ways. They increase the time you spend at chargers, they increase the cost per useful kilowatt hour because you pay for energy that doesn't reach the battery pack, and they can increase the battery stress if the car repeatedly runs heating or cooling cycles that keep the pack at suboptimal temperatures. Studies on preconditioning and thermal management show that bringing the battery to the right window before charging both reduces session time and reduces long-term degradation risk. The opposite, charging while the pack is cold and then using heavy heat power, both slows charge and stresses the cells. That means parasitic loads don't only steal energy power, they can shave life of the pack down the road if you make them habitual. The moment you reclaim your electrons, what works and why? Here's the good news. Many parasitic losses are behavioral or configurable. You can reclaim a surprising fraction of your charging power with a few simple habits and settings that cost nothing but a little attention. Precondition while plugged, use the car's app or timer to heat or cool the cabin and warm the battery while the vehicle is still connected to the grid. The energy to precondition comes from your house, not the battery pack. And it avoids the large thermal draws during the actual charging sessions or initial drive. Studies and owner tests show preconditioning can increase initial charging power dramatically and shave minutes of fast charge stops. Disable unnecessary always-on modes. Turn off sentry mode, valet modes, or app ping features when you don't need them. Recurrence vampire drains work shows these modes cause measurable extra losses and many owners recover miles of range simply by managing them. Use eco-climate or heat pump modes. If your car supports a heat pump, use it. Heat pump deliver more heat per kilowatt hour drawn than resistive heaters. In cold climates, favor seat heaters and steering wheel heaters when practical because they use much less energy than heating the whole cabin. Heat pump-equipped EVs consistently outperform resistive heat cars in winter energy use. Turn off large displays during charging. Dim or turn off the center stack screen if you don't need it in plug. Dim or turn off the center stack screen if you don't need it while plugged. That saves tens to a couple hundred watts and returns energy to the battery pack. Energy awareness displays also help you see what's being used in real time. Research on in-car energy displays shows awareness changes behavior. Schedule charging smartly, charge overnight or in cooler parts of the day to avoid heat soak and lower ambient temperatures. Off-peak charging also often saves money and lets you precondition overnight during cheaper hours. Grid studies and pilot programs recommend managed preconditioning and off-peak charging to smooth demand and reduce stress on both the grid and the vehicle. A quick practical example you can use tonight. Imagine a commute that needs 12 kWh per day. You plug into a 7.2 kW level 2 at home. Without changes, thermal and accessory loads might take 1.5 kW on average during the charge window, leaving 5.7 kW net. To deliver 12 kWh at 5.7 kW takes about 2.1 hours. If you precondition while plugged, so thermal load during the charge drops to 0.5 kW. And dim the screens, which drops the accessory draw by 200 watts. You now deliver 6.5 kW to the battery and finish in about 1.85 hours. That's about 15% time saving and more energy in the battery that you can spend more on the road. Multiply that over weeks and months and the minutes and kilowatt hours add up. Parasitic loads are real, measurable, and often fixable. Thermal systems can swallow multiple kilowatts in extreme conditions. Small electronics quietly steal hundreds of watts. And vampire drain chips away that stored energy when the car sits. These drains slow charging, reduce useful range, and if mismanaged, can increase long-term battery stress. But the toolkit to fight them is practical. Precondition while plugged, use heat pumps and eco modes, disable unneeded always-on features, dim large displays during charging, and schedule charging for off-peak or cooler hours. Do these things and you reclaim time and money and miles.